Good morning, dear student. Welcome to this 18th edition of our Numerical Method 2 class. Today we will proceed with where we stopped last time, that is trigonometric polynomial. A trigonometric polynomial is just a truncated Fourier series. So if you look at the definition, you will see that this is our Fourier series that we truncated. So we stopped after n term. And it gives us what we call a trigonometric polynomial of degree n. So when you hear trigonometric polynomial, you expect maybe to see powers of maybe cosine, powers of sine, or something like that, or to confirm that yes, it's a trigonometric polynomial. Indeed, it's a trigonometric polynomial. If you remember the Moivre formula, what some will call the mover. Anyway, some people have funny ways to call it. This one, the Moivre. Maybe you will call it the mover whatsoever. Okay, this one, the Moivre, is written like this. The Moivre formula some also call it Euler. No. It's a bit different. Euler formula is the other one. It depends. You might have other names. Yeah, I think not. In some textbooks they also call it Euler's, because Euler formula is what we saw in Euler's formula is this the definition of ABs, of AKs and BKs. We call that Euler's formula here. This one. Obviously, if I'm not mistaken, right, I have to. The Moivre formula is also called Euler's formula, right? It's also called Euler's formula, if I'm not mistaken. Let me write it here so that if that is the case, you will not say that, oh, I didn't tell you. I think it should also be called Euler's formula. Formula or identity, something like that. So it will contrast with the previous one. Anyway. So when you have a complex number, remember that you can write a complex number z in a trigonometric form. It has a trigonometric representation. We know that in general, you can write a complex number in this form. And this is an algebraic representation of a complex number. But in a complex form, you can write it as r cosine theta plus I sine theta. This one. So you agree with me that, okay, this is not a formula. This is not a formula. I'm just writing, but now the formula is the following. So the formula is this one. Now, if you want to compute z to the n, like that, which is, of course, is to the n, so that is r to the n. And now this one will be cosine n theta plus I sine n theta. You see that this one already, you can see, of course, if you take the radius to be 1, right? If you take the radius to be 1, now your z to the n will be a combination of cosine n theta sine n theta. So this multiplication of the angle by n is like a power of, it's like a power of, you see, z to the power of. So it is reflected there. So that is to confirm that this indeed is a polynomial, it's a trigonometric polynomial, right? Is that clear now? I'm trying to connect what you know with the terminology of polynomial, trigonometric polynomial, multiplying the angle by k and varying the k that is a polynomial in the same manner that I can write z to the power of n, which is exactly a combination here. You just need, of course, if you don't want this to be a complex number, you just take the real and imaginary part, then you will get rid of the I. You just take the linear combination of that, and then it will give you exactly this. So it's indeed it's a trigonometric polynomial. I hope it's clear now. All right. Is it clear, Aaron Fried? Katuo. Is it clear?
Yes, doctor.
Good, good. All right. Now we are going to do, if you recall what we have been doing previously in terms of least square method, right? We are going to apply the least square method this time again. But we are going to use instead our Fourier, when I say Fourier, our truncated Fourier series, right? To fit the data. So data fitting using trigonometric polynomials will give what we call discrete Fourier series. Okay, so this is the set of data point SKYK. So we have exactly n plus 1 point, and YK represent the value of a given function at xk. The function f is only known at discrete point, but we don't have a representation of that function. So we will try to fit that, that function or approximate that function using a discrete Fourier series. That is, in fact, using a trigonometric polynomial of degree n. You can see for yourself that this is our least square approximation. So we know already from the previous sections that this can be simplified, right? The least square problem can be simplified if we have an orthogonal basis, and we know already that cosine sines form an orthogonal basis. If you recall from here, these are the elements of the basis. Sine nx, cosine mx, all those, yeah. So you can see that they are orthogonal. When m is not that, for sine is 0. For sine cosine is 0. You see, for cosine alone is also 0 there. For sine alone is also 0. You can see there. For cosine is 0. So you can see that they form an orthogonal basis. And we know that when you have an orthogonal basis, you can easily find the coefficient, right? The coefficient easily. So our coefficient here are the AKs and BKs from our trigonometric polynomial. These are our coefficients. We have the AKs and the BKs, right? So we know already from the previous section that if you perform that, you see, it's already there. So we know already how our AKs and BK will be written. We know the expression from the previous, right, from the previous section. So this is exactly the coefficient. They are given by this formula. And that's our theorem. Right. Okay, now let's look at the theorem and let's extract meaningful informations. Okay, now you see that for the discrete Fourier series that we are using, the point, when I say the point, the abscissors, right? The abscissors here, as you can see, xk's are given by this particular formula. So xk is not chosen randomly, but our xk have a particular structure. So we are taking this, and what is our interval? Negative pi, right? That is the interval that we are using, and we discretize that interval using this xk. You can see that when k is 0, the first point is negative pi. And now when sk is n, if we say sk, when k is n, or when k is 0, x sub 0 is negative pi, and when k is n, if you substitute n here, n in the numerator and the denominator will cancel out, then 2 pi minus pi gives you pi. So you see that we take the interval negative pi and we discretize it using exactly this point. Right? So that's our x. Now, the function that we want to approximate, that's our f. So now, the theorem states that if the function is periodic with period 2 pi and twice the degree of the polynomial, remember, trigonometric polynomial of degree m, you can see here, p sub m, trigonometric polynomial of degree m. So if twice the degree of the polynomial that you are using to fit the set of data point is less than capital N, of course, capital N is the number of point minus 1. So if that is twice the degree of the polynomial is less than n, capital N, which is the number of data point minus 1, because the number of data point, if you see, is n plus 1. Okay, so if this condition is satisfied, then we can find Pm that will minimize this quantity. This is our least square error, if you remember. This is a least square error. Right? So it's a minimization. So this polynomial will exist. So the polynomial, the trigonometric polynomial, will only exist if this condition is satisfied. So it is important to bear this in mind. That is a requirement. Twice the degree of the polynomial should be less than capital N, where capital N is the degree, the number of data point minus 1, right? Or one integer less, one quantity less. Okay, and these are the coefficients are given by this formula. Okay, now let us look at an example. So now if you look at this example, we want to use 12 equally spaced points. K equal to 1, 2, 3, up to 12. So we want to use that to find a polynomial, a trigonometric polynomial approximation for capital N equal to 5, right, to fit this set of data points. When our function f of x is given by this, x by 2, right? We know already this f of x by 2. We know we dealt with this one previously. F of x equals to x by 2. I think it was, it's this one. Remember this. So we constructed this one to be x by 2 in the interval negative pi. And remember that we sample our point in this interval, negative pi. That's why we sample our point. So the x case as defined are here, right? So, and we extend this function periodically to be of period 2 pi. Okay, so that's exactly the same function that we are dealing with. So this one. Okay. You know already, I told you in one of the classes that if you have this function and you extend it periodically, you will be getting this, something like this. Oh, sorry. And so forth. And at this point, there will be discontinuity here, at this point. And so forth. So this is something I already mentioned. And those points are what we call A, right? At those points, we have this. And if you substitute, you see that the function will be 0. Obviously, 0. Why? Because the value here and there are opposite, right? So if you add them up, it will cancel out, it will give you 0. And it will give you the average. The average is 0, obviously. So at the point of continuity, the value of the function is 0. Similarly, at negative pi and pi, the function is 0, right? From this. And here, you can see that f of x is defined on the open interval. The interval is open. It's open at negative pi and at pi. The interval is open. And you also know that the function is an odd function, right? If you look at this one, in the interval negative pi, pi is an odd function. That one also we know already. And for that purpose, if it is an odd function, the cosine will all be 0. All right, so these are the information. And therefore, will only involve sine. So this should be sine. This is so oh, very bad. So this is the sine, not cosine, the sine. Please correct that. It only involves sine term because all the cosine coefficients are 0. Right. All right, so this is what we will get if you compute this. If you compute these BKs, you compute all these BKs, you get this coefficient. So how many coefficients do we have here? 1, 2, 3, 4, 5 coefficients. Because K, you see the degree is 5. K start from 1. Here. K takes a value 1, 2, 3, 4, 5. So there should be 5 terms for B. Okay, now I will ask you the question. You see that in order for us to perform this approximation, we use the information about the function. We did not just use the AKs and BKs and substituted the value. You see that if you don't use that information, you will compute blindly this. And there will be a contribution in AK. And if you add the AKs, it will give you a wrong approximation. So Each time you are dealing with Fourier series, first of all, look at the structure of the function. Are you given any information if the function is odd, even, or neither? You think about that. Okay, now, if the function is given and you can look at the structure of the function to see that, no, structurally, this function is an odd function, therefore the AKs are 0. You don't need to compute. Because if you compute using this definition, it will give you non-zero. But whereas it should be 0. So be careful. I think I mentioned that yesterday. Don't just compute the AKs and the BKs. First, look at the function. What information do I have about the function? If I'm told that the function is odd or even, the corresponding coefficient will be set to 0 without computation, because you might compute and get a non-zero. Because the function that is given to you is only valid in a given interval. So don't just try to compute it anyhow. Right. So that's the information about Fourier series that we are using here, because this is a truncated Fourier series. So when you are dealing with, trigonometric polynomial, bear in mind that these are truncated Fourier series. You don't want to use the entire Fourier series. You truncate it to obtain discrete Fourier series. So you see that it's still Fourier series, right? So the information that you know about whether the AK will be 0 or the BK will be 0, all this information, go back to your knowledge of Fourier series to assess whether this will be 0 or that one will be 0 or neither. I hope it's clear. Don't get confused when it comes to this. This is just a discrete Fourier series. Instead of taking an infinite series, you truncate the series. You obtain a sum or a partial sum. Gives rise to discrete Fourier series. And you can see that we use the knowledge of Fourier series that we know. Is that clear? Okay, the other thing we did not check is twice the degree of m less than m. Because remember, that's something we need to check, right? We need to check that. Okay, so our m is 5. 5 times 2, 10. Okay, here we are using a total of 12 points, but remember that's the number of points minus 1, which is 11. So twice 5, which is 10, is less than 11. So we are done. It's correct. Because actually, this is from 0 to, okay, this should be, actually, if you want to keep the correct notation, you can take that from 0 to 11. 1, 2, 11. Right. Or normally, okay, that is, let me, it is, because if you look at this, if you put 2 pi by this one, this should be 12, n should be 12. Look at this. This is capital N, right? Here. I have the 2 here on top. 2 pi, 2k pi by capital N. So if capital N is 12, 12 will cancel out with the 2, then it becomes 6. Then you have k pi by 6. So meaning that our capital N is actually 12. So you stop at 12, but you start from 0. Right? Yeah. So the number of points is not 12, but it's 13. Right? If you apply that, it's 13 instead of 12. It should be 13 here. Because this is our capital N, the last one, and we can see that here, this is 6. The 2 is here, so if you multiply by 2, this should be 12. Since we start from 0, it means that this should be a total of how many points? 13 point, right, instead of that. But still the condition is satisfied. You can see that the condition is satisfied. Twice this is 10, and 10 is less than 12. Where 12 is capital N is 12. So this is our capital N. So capital N is that. So M is 5. Capital N is 12. So we have 2 times M, which is 10, is less than 12. So this condition is satisfied. So after the theorem, this polynomial Pm exists, right? The theorem tells you that that polynomial exists, and it's given by this expression. Okay, so if we plot this is what we have. And remember that our function is this straight line. It's a straight line like this. You see that it approximates the straight line well, right? The actual function f of x by 2. You can see that this polynomial is approximating it well. Okay, so you're encouraged to look at this and try to compute. Please do this. I encourage you to do this. Do this and try to compute using 12 or 13 points, or 12 and 2 points, and then you take 60 points, 360 points. Of course, to do this, you will need a computer. Huh? You agree with me that all these number of points you will not be able to compute this. You just use the B. These are the B, yeah? B, yeah? B1, B2, B3, B4, B5. And now to sum all over this point, you need to write Python code or MATLAB. Then you sum here. Okay, and another remark. Another remark here, in your summation, you can see that the summation starts from 1 to n, 1 to n, 1 to n. So actually, we don't use the case k equal to 0, right? From this formula, you can see that. I think I still have the code, because last year we wrote the code for this. Was it last year or the year before last? If I check, okay, let me check that a bit. Huh? Let me check that. Okay, so we are done with this first part. This is the very last part, right? So the test will be everything except this last part on trigonometric polynomial. Yeah. Okay, but now let me look at because I think I will give you after the next. I might give you an assignment on this one. Anyway, I will see. Well, should I give you an assignment to write this code? Okay, let me look at the code. Let me check first. Huh? Let me check to see. Because I remember we did that, but where did I save the code? I'm not sure I will recall that exactly. Okay, I don't see it here. Okay, but in the meantime, if there's a question you can ask, I'm trying to locate where. Is there any question? Any question, any concern, even if it's not related to what we just covered, even if it's from the previous section, you can ask your questions. Yes, guys, I'm listening. I'm listening. I'm listening. Who has a question? Okay, I haven't found that, but if I find it next time, I think I will share that. So far, I don't know where it's stored. Where is it that? Yes, 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 yes. I'm listening. Ask your question. Eden Fried, ask a question.
No question, doctor.
Sorry?
I don't have a question.
Do you have an answer?
An answer to?
To a question, if I ask you a question.
I hope so.
Huh? If I ask you a question, will you answer? Simeon, do you have a question? No question. John has a question. Do you have a question? Shona, do you have a question?
No, sir.
What do you have? Camelo, no question?
No, I don't have, doctor.
Class rep, no question?
No question, sir.
Okay, everything's clear. Okay, so we stop here. Thank you for your kind attention. God bless you and see you next time. Bye-bye.
Bye, sir.
Bye, sir.